Manuela Bonanno from Columbia University. I'm here sitting with Michael Abend. Hi, Michael.
Hi, Manuela.
Please introduce yourself, where you work, and what's your institution and your position.
Okay, so my name is Michael Abend, and I work at the Bundeswehr Institute of Radiobiology, which is located in Munich. And I work there as a radiobiologist. My background is medicine, radiobiology, and epidemiology. I had the chance to do some epidemiology also at the NCI, the Radiation Epidemiological Branch, and I'm always happy to see these people again at these meetings. And my actual position at the Institute is Deputy Director, but even more important, I'm leading a group working in the field of gene expression.
Gene expression. So that leads me to ask you, what's your line of work? What you say you coordinate people, so what's the project or?
Yeah, actually I would like to tell you a little bit about the background. Why are we doing gene expression? Yeah, so we are.
Context?
Yeah, the context. I think the context we should start with. It's very, very important. I think Stephen Simon just recently in the meeting made a strong statement regarding what will happen within the next 5 years, or what could happen in the next 5 years related to radiation research. And he said, or he pointed out, well, we might face the opportunity, the possibility of a terrorist attack.
Unfortunately,
and this is also something we are very scared about in Europe. We have some networks dealing with this, but of course we have to be somehow prepared. And this is the context of our work. So we had the option to do a collaboration with our French collaboration partners. They are doing animal work. It's very difficult, very hard to do animal work with non-human primates in Germany. So we got the opportunity to get some blood samples from baboons irradiated in France. And
what kind of irradiation, or I mean, which kind of terroristic scenario are you trying to mimic or study?
Actually, the baboons were irradiated with partial body irradiation. The equivalent dose was either 2.5 or 5 gray. It was altogether 18 baboons only. And that's the limitation of our study, of course. And all of these baboons were irradiated in different ways regarding the partial body radiation.
Can you give me more details?
Let's say something like 5 gray radiation exposure of 80% of the body, except shielding of one arm or something like this.
So different combinations.
It was different combinations, and they were very much focusing on partial and total body radiation exposure. And this is also something, it's an interface in our society, a very strong interface in our society. Radiobiology on the one side and physical dosimetry on the other side. And there is another interface which is really missing in our field of radiobiology, and that's the interface to medicine. I mean, these baboons, they got a different radiation exposure, and depending on the radiation exposure, some of them developed a more severe or less severe disease, which is called a hematological acute radiation syndrome. And according to Metropol, which is a European-driven kind of system to divide the ARS, hematological acute radiation syndrome, into certain severity degrees. So what?
Like in stages.
Yeah, right. So we were interested not as much, we did gene expression measurements on these baboons, and we did this very early after radiation exposure, during the first 2 days after radiation exposure.
That's, if I can interrupt, that's when you are interested in understanding whether somebody has been exposed, right? Because in a case of a terroristic attack, you first have to understand whether that person that comes at the emergency has been irradiated, and if so, what's the dose, right?
Exactly. This is because of diagnostic purposes. So just imagine there is a terrorist attack, yeah? Then you cannot hide that some radiation exposure was happening, yeah? So many people, a lot of them will go to the hospitals, yeah? And then the hospitals need some diagnostics, some early and high throughput diagnostics in order to select those individuals who later, within days or weeks after radiation exposure, will develop the HARS, a more severe or a mild. So there's two questions to be answered. First, do an early diagnostic as fast as possible, and second, it should be high throughput, and you have to make two medical decisions. Hospitalization, first part, which people have to be hospitalized and which people not. Mm-hmm. That's very important. The void wells, yeah, those individuals who believe to be exposed but who are not. The one part are those who got a low exposures and would never develop an HARS. They have to leave the hospitals in order to have some place, yeah, for the HARS. Right, who needs it? And we are talking about intensive care units, yeah, and it's a very difficult thing to treat these people, these victims, developing the HARS, and therefore you have to do a selection, a triage, and for this you need a good diagnostic tool. So,
and you were saying that your diagnostic tool of choice is gene expression?
Right. And that's also a little bit of challenging, because with gene expression after radiation exposure, you see some changes in gene expression.
Many genes.
Of course.
Many genes.
And they change over time.
Right.
So that's the one thing we have to take care of it, yeah? Select those genes which are hopefully consistently up or down regulated over time.
And eventually are up regulated or down regulated, even depending on the dose that the person has received.
Right.
That would be.
But thank you that you're saying this, Manuela, because we are not interested in dose anymore. We know the dose in certain individuals, they got the same dose, well, 2.5 or 5 gray. Some of these baboons irradiated with 2.5 gray, they developed a severe HARS, but some baboons irradiated with 5 gray equivalent total body radiation did not develop a severe ARS. So the dose helps you in a certain way, but it would be better to predict the effect. Predict the effect, not the dose. Yeah, that's important.
Because I think probably this relates to the fact that people, if there is an attack, they might be exposed, like you were saying, probably somebody would get the 5 gray 80% of the body, some other just one side of the body, because there might be a shielding, a building shielding or whatever. So it's more, you are after more to the effects.
Right. Okay. So actually with these 18 baboons, these partial body radiation exposures, this was a good example, so to say, for that what we are scared about, a terrorist attack, and this is probably related not to a homogeneous irradiation.
It cannot be. I mean, realistically, it won't happen, right? Yeah. So
let me tell you a little bit how we came up to our something like 30 candidate genes, and so we did a whole genome screening, taking a part of these individuals, and that's also something I have to say, and I didn't say so far. We also got biosamplings, peripheral blood, before irradiation. So this was, so to say, our control.
Baseline.
Yeah. So this is the unirradiated 18 baboon, so to say. And then we had these peripheral blood samples from the first and the second day. And then we tried to see an association with the severity of the late occurring HARS. So we took part of them and we did a whole genome screening, taking advantage of this microarrays.
Yeah, you were talking about high throughput
Right.
assays. So
yeah, but the microarrays, with regard to high throughput, they are not so nice. But I would like to, the QRT-PCR is better for high throughput. We can do 12,000 measurements within 2 hours with the QRT-PCR. So that's, with the microarrays, the hybridization takes a lot of time, takes something like half a day. You can overcome this, yeah? So this takes a little bit too long, but with QRT-PCR, you're much faster. But let's start with the microarrays. First, we had to find out about the candidate genes. Right. So we start with the microarrays. The microarrays cover the whole genome. It was 60,000 transcripts, which were covered by this microarray we used. Then we came up with some candidate genes, and these candidate genes were then selected and they were validated with another methodology and on the other samples. So it's a strong, it's the, well,
reliable.
Yeah, it's the most robust validation you can think about. You change the methodology from microarrays hybridization to QRT-PCR using Techman chemistry, yeah, which is the best on the market, and then you try to find, you do this on this other sample, so it's an independent validation. So we came up with these genes, and just look at the poster. I'm so impressed. I never in my, I'm doing this for 12 years now, and I never got such a clear and robust gene signature. Never. And never afterwards, unfortunately. Yeah. So we continued with this research. So that was just impressive. So we got something like 30 candidate genes, and now we are validating this. But validation is very difficult. You can try to validate it in another species, another non-human primates. We are working on this, but it's very difficult to find partners.
Of course, and I imagine, first of all, because it's a very expensive study. So
yeah, but also work on non-human primates, and you know, there is ongoing work on these primates, and to say, oh, can we get something like 2.5 mil? That's very challenging, yeah, because people are scientists, yeah, they already checked for every mil of blood what to do with it,
yes,
yeah, and then a guy from Germany says, oh, how about 2.5 mil blood?
It's a little bit too much.
Yeah, it's a little bit, yeah.
Yeah.
Well, we could reduce it a little bit, but it was a little. But there is an alternative.
Which one?
Use the human models. Patients, they get treated because of leukemia, and then they got a total body radiation. They got something like it's a fractionated radiation therapy. They get something like 4-grade TBI. And
but aren't you afraid that they are going to have some pre-existing conditions?
Very much so.
So how would you?
You have to.
There are ways to take those in account?
You have to consider this. For instance, WNT3, our hottest candidate, yeah, it's downregulated up to 30-fold mean on average related to the H0, to the controls. So yes, it is downregulated. So with this leukemia patient, I would expect the same. It should be downregulated. Yeah. So they are already leukopenic when the controls we get from the patients. Let me put it this way. Yeah. Before irradiation, they already got some treatment, and therefore the leukocytes are already down. Yeah. So then they get the radiation exposure. So what we expect, it's not a 30-fold down, regulation of the genes, but it should go in the same direction.
Right.
Yeah, whether it's 5-fold, whether it's 2-fold, I don't care, but should be the same direction. And this is the way it works. And although the number is not very high so far, but we took 6 of these candidate genes, and 5 of them already show the same pattern. And that's wonderful. So we are very happy, and we think we have something in our hands. Well, we have to continue with this validation, but the first results look very promising, and now we're looking for this other prerequisite of this kind of diagnostics. It works early after radiation exposure, as expected, before the drop down of the lymphocytes, the granulocytes, and so on, which is regulated on the transcriptional level. We see that happening, yeah, or in the first days after radiation exposure, it starts already there before it drops down. So this concept, it worked, yeah, and now we have an early diagnostics tool, yeah, developing, yeah. But then the high throughput is the next part, and within the next year, we'll work on an exercise where we will process 1,000 blood samples, and we want to see whether we can get an estimate of the HARS within the first 24 hours after radiation exposure. So we are trying...
Always following these 30 genes.
Correct.
Yeah.
And that is that.
That is that. I just have another quick question. If you can tell me more about these 30 genes, do they belong to specific pathways? Are they related to each other in a way?
Actually, yes, it's related to immunology, yeah, and it's WNT3, for instance, is related to developmental processes. And we were wondering about this. I mean, developmental processes and then radiation exposure. Yeah, that was very surprising to us. Yeah, we saw it was in mice. We did a literature search, of course, yeah, because we were wondering whether what's known about these 30 genes about we detected, and only 6 of these genes were already somehow related to radiation. Yeah, of course, in the genetic banks, yeah, they are characterized. They are coding for immunology, developmental processes, as I mentioned, but not related to radiation exposure so far. So we were scared that something was wrong, but then our results were so clear. Yeah, so I couldn't believe this. So yes, that was still, it was very, it was, how shall I say, we didn't feel very comfortable to see, oof, this is the genes which are really new to the society, but with the first preliminary results on the validation using human samples, yeah, I feel much more relaxed, as you can see.
I can see, and yeah, so I think I look forward for the next year or two to read more about your research, and probably you will tell us about the other 24 genes, and those are like new genes that we as a radiobiologist
if I get another
into.
chance for an interview, I'll do so.
Okay, so see you next time, and thank you very much, Michael, for taking the time to talk to us.
Thank you very much.